So by the 1970s, say, after the discovery of the cosmic microwave background, the successes of Big Bang nucleosynthesis, doubts about whether the Big Bang was a real event had pretty much been dispelled. But the idea that we could actually make precision measurements of the cosmological parameters seemed far-fetched, so people played around with models mostly based on their theoretical biases. The situation has changed drastically in the past few decades, and the first precision measurements of cosmological parameters were made by measuring the anisotropy in the cosmic microwave background. Remember that in the 1990s, the COBE satellite produced the first anisotropy. It detected the motion of Earth through the cosmic microwave background. Subtracting that, you see that even absent Earth's motion, this is sort of taking into account Earth's motion, the microwave sky is not completely isotropic. This, remember, is the structure of the universe. This is telling us something about the way the universe was when it was 380,000 years old. This is the oldest light we're able to see. These are, if you want, a pattern of some inhomogeneities in the universe, which hopefully later led to the production of galaxies and clusters and so on, because the universe today is certainly not homogeneous. This was very exciting. We could learn a lot from it. In fact, a follow-up mission, later renamed the Wilkinson Microwave Anisotropy Probe, was launched, and you can see that WMAP produced a far more detailed image of the sky. And what is it that we learn from this picture? So we see regions that are hotter and regions that are colder. What is it that we learn from this? Well, the first thing is, again, analysis of essentially the spectrum of fluctuations as a function of angular variation. So over what angular ranges does the temperature of the microwave background, what that map is the effective temperature. So there are regions that are slightly hotter, slightly cooler. And what we see is that at large angles above about a degree, there's very little correlated fluctuations, no large splotches other than the galaxy, of course, in the middle that gets in the way. But at a range, at an angular size of about a degree, there's a large amount of fluctuation. And then at about a third of a degree, and again at about a quarter of a degree, and to a less extent at about a tenth of a degree, there are smaller peaks. But let's focus for a moment on this main peak, which is the dominant peak. The dominant size of angular features in the microwave background is a degree. What does that tell me? Well, what is this? These are the images, I claim, of density or sound waves in that primordial plasma at the age of 380,000 years after the Big Bang. How does this work? Well, you'd expect that there can be sound waves in a plasma. Some region, by fluctuation, becomes dense. It becomes hotter because of the compression. The heat generates radiation pressure that expands the region again, and you get this sort of oscillatory wave behavior. Two things to take into account. One is all of this is dominated. This plasma is gravitationally interacting, and it's responding to the gravitational pull of the much larger concentration of dark matter that is around. And the other thing is that, in fact, denser regions show up as colder in this map of the sky. The reason is indeed they were a little bit warmer, but this is overshadowed by something called the Sachs-Wolf effect. Denser regions are deeper gravitational wells. The gravitational redshift of the photons emerging from these denser regions is larger than that from less dense regions. This overwhelms the actual heating of the local region. So in fact, the colder regions in the microwave sky represent denser regions. But be that as it may, we are mapping essentially the density or temperature fluctuations of the universe at 380,000 years, and we're mapping these sound waves. Now, what do you expect the wavelength of these sound waves to be? Well, it turns out that we have a very good prediction for what the typical wavelength of such a sound wave would be. The typical wavelength, it turns out, is of the order of the distance that sound can travel in that plasma in the time, 380,000 years, that the universe had existed. Certainly, waves with wavelength larger than this should not exist, because the wavelength, basically the size of a peak, a region that can coherently fluctuate to higher density without dissipating, should be limited, just as we have in the past used the speed of light. Here we're using the speed of sound to say that different regions can communicate with each other by the speed of sound, and this means that the wavelength that you expect should be smaller than or equal to, the distance that sound could have traveled by that time in the age of the universe. Now, the speed of sound in this dense plasma is very high. It's 1 over square root of 3 times the speed of light because of the properties of strongly interacting plasma. And since we know the distance that light could have traveled by this time, that is the horizon distance, we're in a matter-dominated universe. We're talking about 380,000 years, so it's after the 55,000 year radiation to matter domination. The horizon distance at time t, the distance light will have traveled since the Big Bang, is 3 times c times t. Since sound travels the square root of 3, 1 over the square root of 3 times the speed of light, the wavelength we expect is 1 over square root of 3 times this, or this is our wavelength. You can plug in the numbers. We know the time, 380,000 years. It turns out that we're talking about a wavelength of about 201 kiloparsec. So these are very long wavelength oscillations in the plasma. Now, we are looking at this at a coordinate distance. This happened at some place, and the coordinate distance that light travels in the time from this time to our time, you can compute that using our understanding of the expansion of the universe. The distance time travels between T ionization and T0 is given by this expression. It's this 1/3 power. You can recognize at least that if I set T ionization to 0, the time that light has traveled since the Big Bang in this dust-dominated universe is 3ct. Doing this calculation requires an integral, so I won't drag you through it. But since we know that A of t during the dust-dominated era is given by A0 times t over T0 to the 2/3, I can replace T ionization over T0, and A0 is 1, by A ionization to the 1/2, because I substitute to the power 1/3 to the power 3/2 to get 1/2. So I get this expression for the coordinate distance. What is that? That is the distance today of the place from which we are seeing the cosmic microwave background. You can evaluate this, and we will later find a number. But for now, I want the expression. So what does this tell me? Well, what does this predict about? I have the wavelength. I have the distance. I want to predict the angular size in the sky. Small angle formula. Let's use the small angle formula. I'm going to use the small angle formula, assuming the universe is flat, remembering that the angular size distance is coordinate distance today, divided by 1 plus z, or multiplied by the scale factor. So I plug in what I had. The coordinate distance is this. The wavelength is this. The redshift, 1 plus the redshift is the inverse of the scale factor. I evaluate this. The scale factor at ionization is 1100. Plug in, you get 1 degree. So what I have is that if I remember to apply the geometry of Friedmann-Robertson-Walker, and I assume that space is flat, I predict the correct angular size for these acoustic waves in the plasma. In other words, we have just proved the space is flat, because remember, what I used essentially in the small angle formula is the idea that geodesics are straight lines and triangles behave as they should. If the universe, for example, had negative curvature, then the small angle formula would be ruined. Theta, as observed, would be smaller than a degree that you would predict from the flat universe for a given size, whereas if the universe were positively curved, I would observe a large angle corresponding to the same triangle. And so the fact that we obtain agreement is very strong evidence that space is flat. Here's this rather undramatic, because realistic, representation of the triangle in a negatively curved, or as they call it, open universe, and you would predict a smaller angle than the angle that we found. And so when I said that I know that the universe is rather precisely flat, I have managed to draw an actual triangle whose base I know from other considerations, whose length I know from other consideration, compared to the small angle formula, and I've measured the curvature over a distance of about 16 billion light years. That's a pretty good base, so I am constraining the curvature of the universe to be almost precisely zero. This is why we know space is flat. There is more structure, obviously, than just the first peak. There are these subsequent peaks at smaller angular distributions. First of all, there's the total absence of any fluctuations larger than a degree. This makes sense. We said fluctuations larger than this could not have formed because distinct regions within the same wave were outside each other's particle horizon, could not have gotten together a coherent wave. Understanding the subsequent peaks, you have to take into account, as I said, that the sound is sort of controlled by the density fluctuations of the dark matter. It turns out that the height and position of the second peak are sensitive to the baryonic dust density. The third peak, relative to the second peak, its height and position, are sensitive to the density of dark matter. That's a little bit technical for what we're doing, but by combining observations of all the spectrum, we can learn information both about the total density. Remember, we have discovered that the universe is flat, so omega is essentially 1. That explains why I am so confident that omega, dark matter plus dark energy plus normal matter, adds up to 1, plus radiation, which is very small. And furthermore, the ratio between dark matter and baryonic densities is further constrained by this measurement, together with nucleosynthesis. We are beginning to get a handle on the precise values of these parameters. Lots more information can be extracted from this cosmic microwave background, and is being extracted, and more is constantly being done. Polarization data, analysis of the interaction of the background radiation with galaxy clusters. There is a lot of information, and you can go to the WMAP project webpage and learn what else we can learn from